it is Wednesday the 14th. It is Bastille Day. I just realized that. And we are going to talk about atoms and matter. And for those that haven't realized, yes, I'm a huge history buff to the point that I didn't realize I was off mute, and you guys got to hear me listening to jamming to literally history metal. So that's kind of amusing to me. I was like, oh, look, I'm off mute. I totally did not realize that. But we're going to talk about atoms and matter today. And some of this is going to be rehashed from what Dr. Johnson talked about. And then some of it's going to be some new stuff that goes with physics. So we're going to talk about atoms, molecules. We're also going to talk about some very common molecules in physical therapy that we're going to deal with. We're going to talk about the properties of matter. And this is why it all should matter to you. So you guys talked briefly about this in anatomy, where you talked about this periodic table here. And the periodic table is all of our known elements, right? And when I say known elements, these are ones that we can identify. Are there probably more elements out there in the universe? Probably. We just don't know about them yet, right? We could land, you know, the rover that's on Mars right now could find a brand new element that we're not aware of. And that would have to get added to the periodic table somehow. We just don't know. We may just not know about it. It may not exist on our planet. Ironically enough, what we're finding is most of the elements that exist here on Earth are elements that exist on Mars as well. So, you know, there's a lot of linkage between our planet and a lot of the other planets. You know, we know looking at things like Titan, right, which is a methane gas ball, or looking at something like Europa, those different moons. We know they all have. When's the last time we found an element, Mark? Is that what you're asking?
Yes.
Yeah, so the last one I believe is nobelium. I'm not sure when did, let's see, I want to say it was 1992 is when nobelium was found. Let's see. I'm actually curious now because I want to see if I'm right. When did we discover nobelium? Oh no, wow. So the last time the periodic table was updated was 1963. That's kind of crazy. Like, I thought nobelium was a newer one, but I guess 102 was kind of the most recent. And one of the reasons why we are not discovering new elements is because once you get up to that like 100 plus range with protons in the nucleus and electrons in orbit, they become very unstable. Like nobelium itself, I don't believe exists in nature. We've created it. We've created a stable molecule of it, but then it undergoes radioactive decay, right? And will decay down to, was it mendelevium, which decays down to fermium, which decays down to californium, and keeps going backwards until we get typically to either plutonium or uranium, which is where those kind of nuclear materials we're going to talk about creating energy. Most of the elements we deal with in nature, right? We have our noble gases and our solids like carbon and stuff like that. Those are the primary elements that exist in nature. I want to say that well, actually, I guess 112 is the highest. I went the wrong way. So unobtainium, I think, or unibibium or something. I forget what that one's called. Maybe that's the one that was discovered in 92. It's been a while. I'll have to look that up. All of these exist. Not all of them exist in nature naturally occurring, but they may decay down to something that's a little bit more natural. We're not going to deal with any of those nuclear substances. Good news. That's not something we do in PTA or PT. So we don't really have to worry about that. It's if you get up into high level physics or stuff like that, or if you decide to go work at the CERN collider in Switzerland, then maybe you'll encounter some of them. Those things interest me because, you know, next year we could collide two elements together in the CERN collider and create a new element. And those things both excite me and terrify me at the same time, because I know one of the things we're looking at in the CERN collider is looking at creating dark matter, the opposite of matter, right? And we know that if we have dark matter and matter in the same confined space, bad things happen. I'm like, do we really want to create dark matter? I don't know about that. Seems like it's just a bad idea. we've all seen, what was the movie from, what was the book from Robert Ludlum? Angels and Demons, that's what it was. Yeah, where they talked about how the dark matter flew up over Rome and stuff like that. Yeah. So when we have a substance that is comprised of only one kind of atom, carbon, oxygen, stuff like that, that substance is an element. The atom is the individual unit. The element is when it's composed of one substance. Like one of the big ones that we have to deal with in our world is O2, right? That is what we breathe in and out, and that's what keeps us alive, right? We use oxygen to oxidize stuff in our cells in order to provide energy for us. So we've organized those elements in that periodic table of elements. We know about 115 are known, 90 occur in nature. The others are produced in laboratory and unstable. There we go. I had it on the sheet if I just read it. Associative knowledge of these elements can be important as you start your career because we will use some of these elements. And I created a spreadsheet, which I'll bring up here towards the end, that has all of the chemical compounds you guys will really need to know for your jobs, per se, that cover stuff. So these are the elements that we typically encounter or we talk about in the physical therapy world, right? We're going to talk about sodium, potassium, and calcium. Well, why do we talk about those? Well, those elements all help make up some of our electrolytes. And electrolyte is dealing with the electrochemical signals in our body, right? So you guys should start learning about soon the sodium potassium pumps in the muscles and the nerves that allow conductivity, right? We all have encountered a time where we were low on potassium. What happens typically when you're low on potassium?
Cramp up.
Yeah, you cramp up, right? Exactly, right? So what that is those sodium potassium pumps in that muscle can no longer open up as smoothly. And so you start cramping up a little bit. Sodium goes a long way, right? Sodium can be both good and sodium can be bad. Too much sodium causes us to have high blood pressure. Chlorine as well. We're going to use sodium because sodium itself, if we put it in our body, if we just took the pure sodium and put it on our body, it would explode. Bad idea, because sodium doesn't react well with fluids, especially water. But if we combine sodium and with chlorine, we now create a nice stable compound that we can then break apart the sodium and use it, right? Like a snail, exactly, right? Carbon is another one out there, and I like that Dr. Johnson talked about things being organic, containing carbon and hydrogen, right? Which always kind of amused me. This is one of my one of the things that always amused me when I go to the store and I see things that say all organic lettuce. Well, technically, by science's term, all lettuce is organic because it's comprised of carbon and hydrogen chains. So really, you could, oh God, now my camera's flicking out. Sorry about that. You could call every single piece of food that you get organic. I mean, technically, Hamburger Helper is organic. I wouldn't classify it as the healthiest stuff for you, but it's comprised of carbon and hydrogen. So technically, it's organic. Nitrogen, we have that in our blood, and sometimes we can have too much of that in our blood. Titanium, we use in a lot of our joint replacements because we used to use stuff like ceramics. Like, I'm not joking, back when I started, way back when dinosaurs roamed the earth, a lot of our joint replacements were made of ceramic. And main reason is ceramic is very smooth and allows for a nice joint surface to kind of move over each other. The bad part about ceramic is it's a form of glass and can break really easy. So we're like, hey, let's find a substance that's a little bit stronger than that still has a smooth surface. Well, along came titanium. Iron, as we call it back where I'm from, iron area. Iron is a substance that we use that helps us transport oxygen, right? Our hematocrit and our hemoglobin are really, really sensitive and respond to iron in our blood. You've all probably heard somebody say that I'm anemic, I'm low on iron. Has anyone heard that before? Or somebody say that, oh, well, you must be anemic, you've got to take up your iron, right? Technically, anemia doesn't mean you're low on iron. What it means is you're low on red blood cells. You're low on hematocrit and hemoglobin. Well, how do you kick that up? Well, iron helps kick that up into high gear so that you increase your overall H and H counts. And that means oxygen transport is better, which means you feel better, right? The reason why an anemic person kind of starts feeling like crap is, well, if their red blood cell count is low, well, then that means oxygen transport is low. And that also means then that they don't have as much energy to do stuff. Does anyone know what we use silver for in physical therapy? Other than killing werewolves? Thank you, Underworld. Silver has some unique properties that we really like in physical therapy. It's a couple of different reasons. We found that silver is a very, very pliable metal that we can use to make things called silver rings. And what silver rings are is a set of concentric rings that we can put out a finger if a person's got a contracture on their finger. And that silver ring, as we put it on their finger, can help keep them into extension. So there's one. The other thing is we found out silver is very antimicrobial. So, for those of you that ever consider getting married, maybe consider getting a silver ring instead of something like platinum or gold, because it is antimicrobial. That downside is the tarnish is really easy, right? But a lot of our wound care dressings is impregnated with silver. Now, it does increase the cost of those wound care dressings, obviously, right? But it does actually allow for those dressings to be a little bit more antimicrobial, meaning viruses, bacteria, and fungal infections don't tend to then adhere to those wound beds. So we use silver a lot for that. Magnesium, again, another typical substance we use to help control blood pressure as well as heart rate and stuff like that. Barium, you most times hear about barium when we're talking about swallow tests, right? Barium is a nuclear material that a patient can take in that basically lights up their body. It's reactive to x-rays. So maybe some of you may have had that before, where you've had a angiogram or an arteriogram where they've injected you with that dye, and that dye lights up your vessels or lights up your heart if you're looking at a cardiogram. And what that dye does, it's a variant of barium. There are a couple other ones they use too. Cesium's one of them. But it basically reacts with the x-ray, and when that x-ray hits you, your heart, all the blood vessels in your heart light up, and everything else is kind of dark, so they can see if there's any blockages in your heart or your brain or wherever else they're testing. Cobalt's out there. I don't really use a lot of cobalt. Zinc I do use. Zinc also helps with colds as well. There is some antiviral properties with zinc. There's some studies that have shown that if you take zinc when you have a cold, it does reduce your overall effect of cold. The zinc can also be used in certain substances we use to soften bone and things like that. And then we have, of course, our hydrogen and oxygen, which make up most of what we have, and our H2O. But funny enough, if you have iron, right, I'm going to ask you a question. And you take iron and you link it in a wheel like this. Does anyone know what this is?
Iron Man's chest.
More than that, that's a Ferris wheel. No, huh? Iron, Fe stands for Ferris wheel. Okay, fine. It hits better. Okay, some of you got it, okay. These are the chemistry jokes you guys will have to put up with pretty much for the rest of your career with me. So here's some common compounds that we're going to use in physical therapy. Now, I have them down here for iontophoresis. We're going to talk about that in a second, and phonophoresis, so we also use this in. So usually this is the point where somebody in this class freaks out because they see that I put this chemical compound list here. And they're like, oh God, do I have to remember that, Mr. McKeever? No. Relax. I'm not going to ask you to identify a compound by its chemical makeup. Don't worry. I'm not that mean. I just put this on here so that you can see how complex some of these compounds are. Like, to me, dexamethasone, C22H29, F05, I'm like, God dang, that's a lot of atoms combined to form that compound, right? But we use these. Does anyone know what iontophoresis is? Has anyone seen it? Maybe has been attacked and saw it before, or heard of it maybe? Oh, wow. So when you see ion, what I want you to think of is ion means, that's what I'm going to talk about, Jimmy. You're close. That's phonophoresis. That's what I was going to kind of break apart here. So there are two different techniques we use these medications for. There's iontophoresis and there's phonophoresis. And so I want to break these down and kind of get you to think about this. Ion means charge. Literally, that's what an ion is. It's a charged element. So that means iontophoresis is delivered with E-stim. You guys are going to learn all about E-stim next semester. Phono means sound. That means that's delivered with ultrasound. And we can deliver these medications both with ultrasound and with electricity. So what would an iontophoresis machine look like? Well, typically it's a patch. You have two patches. You have a charge patch, which you put the medication on, and then you have a opposite pole patch, which is going to be obviously the opposite pole. You're going to put all the medication on that pad. You're going to put it over wherever the area is. Maybe you're doing it for lateral epicondylitis. And put that pad over that area. You're going to hook up the pads to it, turn on the E-stim, and the electricity from the E-stim is going to drive the medication into the skin. Ultrasound works pretty similar. So ultrasound, instead of using electricity to drive it into the skin, ultrasound is going to use sound waves. So it's going to use a little bit shorter wavelength wave and allow sound waves to kind of push that medication into the skin. Both of them are going to deliver these medications to areas that we need stuff. So for example, acetic acid. Here's one of the big ones, right? I've used acetic acid quite a bit. Does anyone know what acetic acid is? Because probably most of you have that in your kitchen. I'm guessing most of you. I know I have 3 bottles of it in my kitchen. Acetic acid is nothing but, nope, not baking soda. Close. Good guess, so Josh. It's vinegar. So funny story about it, a vial about this big of acetic acid costs about $60 at the pharmacy. And it's nothing more than white cider vinegar. And you can go to like Albertsons and get a huge bottle of white cider vinegar for like 99 cents. And it's literally the same chemical makeup. They'll say, well, the vinegar that's coming from the pharmacy is sterile. I'm using it to break up bone. I don't care if it's 100% sterile, right? It's going to be sterilized by the E-stim or the ultrasound that I put in anyway. But acetic acid we use a lot of times when we have a calcification. So we have bone buildup where we don't want it. So maybe you've got a bone spur on your heel. In this case, myositis ossificans, this is where a muscle becomes bone. And you're going to learn about that next semester. That's not a good idea, right? Josh, you wouldn't want your biceps to suddenly start becoming bone. Would that cause you some problems? Just a bit, right?
Yeah, probably.
Yeah, not a good idea. You're not going to be curling anything at the gym anytime soon. So this helps break up that bone and I always have students when we talk about this, when we're starting to do stuff like we're talking about E-stim and phonophoresis and stuff like that. Well, Mr. McKeever, does it destroy the bone? Well, no. What it does is it softens the calcification so that the body can then send in those white blood cells, those phagocytes, eaters of the dead, and come in and clean it up. It makes it a lot easier for the body to break down that bone that shouldn't be there. Calcium chloride, CaCl2, used for scar tissue, keloid scarring, and we can also use it for muscle spasms. So I've used calcium chloride in treating a kid with spastic CP, where he literally had really spastic biceps. And we did some phonophoresis and put a little bit of that calcium chloride on it. And we know that calcium is one of those elements that helps us keep from having spasms. we're supposed to take in calcium every day by drinking milk, right? And it helped relieve some of the spasms or calm them down. Copper sulfate, CuSO4, can be used for fungal infections. I like using copper sulfate because it's blue. Like that's one of the few chemicals I really kind of enjoy because it's like this bright, just blue substance. Most of you, if you've ever had athlete's foot or jock itch or any type of fungal infection like that, have probably used some form of copper sulfate because most of the stuff like Lotrimin, can't even think of what some of them, Tinactin, have a little bit of copper sulfate in them because it helps clear up fungal infections. Dexamethasone, this is probably, if there's one that I would like you guys to remember, this is probably the one I want you to remember because that is probably the #1 thing we use in physical therapy. Dexamethasone is a non-anabolic steroid. So we use it for inflammation. So say a patient's got a really inflamed shoulder, maybe because they tore a rotator cuff, maybe they've had surgery, something to that effect. We can use dexamethasone either via phonophoresis or iontophoresis, deliver that medication to that shoulder, and it calms down that inflammatory effect. And maybe get them out of a chronic inflammation cycle where that inflammation has gone crazy. Iodine, we can use on scar tissue and adhesive capsulitis. I've never personally used that. I've only used iodine in wound care to help prep an area that a surgeon's getting ready to do stuff. Because iodine also helps with that. We also need iodine because iodine helps prevent radiation sickness. And way back when the Cold War started with Russia, we realized that we needed to get more iodine in the population. So we had to find a way to get iodine in the population so that if in case we ever had a nuclear missile strike our shores, our population had some natural defense against that radiation sickness. So how do we get iodine into the population? A little bit in water, good. A little bit, very small amount in water. There's an easier way we got it. Salt. Yeah, Josh has got it, right? Because like, how many of us don't love salt? I'm just saying it. Like, I'm one of those people that I see the salt on the table. I'm like, yeah, I could take a little bit of that. But yeah, a lot of our salt is iodinized salt. And, people are, oh, well, iodine, they're softening our stuff and blah, 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 blah. No, and it doesn't soften your interiors. But it does help keep from maybe potentially having long-term radiation effects. A lot of people that work in nuclear plants and that may have additional iodine supplements so that they don't get problems with this. Lidocaine is an analgesic, which means it's a pain reliever. Probably some of you have used lidocaine at some point in your life. Maybe used an Aspercreme with lidocaine, or I think Salonpas makes one now with lidocaine in it. Lidocaine is a numbing agent, right? What other numbing agent have you heard of that starts with cane or that ends with cane?
Cocaine.
Cocaine, okay, yep, there. I wasn't quite going there, but yeah, Novocaine, there we go, right? But yes, believe it or not, Novocaine, lidocaine, and cocaine aren't that far apart. I'm just saying, right? Because and it's true, like for those that, or so I've heard, I will talk a lot about drug use. I just want to be straight. I have never used an illicit drug in my life. I just have friends. I'm just saying I have friends. Honest, I just have friends. And I've heard that if you snort cocaine, your nose goes numb. Well, that makes sense. It's it's a chemical difference from lidocaine to Novocaine to cocaine. And funny story about cocaine. Cocaine actually used to be in Coca-Cola, but that was good. When the good old days happened. Maybe we don't need that in America. Could you imagine if they still had cocaine in Coca-Cola? Good Lord, that'd be bad. Magnesium sulfate is really good. I've used it for ischemia, where patients having an area of localized lack of blood flow. It can help with reducing the vasospasms in that area and allowing the blood vessels, those smooth muscles of the blood vessels, to pump a little bit better. Salicylates or salicylic acid, I'm willing to bet probably a few of us have that in our medicine cabinet right now. Because what do we use salicylic acid for commonly? It's probably in your medicine cabinet if you have it. Yeah, skin, right? Exactly. It's used for a lot of acne treatments, right? It can also be used for plantar warts or warts in general. All that compound W is one of the big ones that uses salicylic acid. If you've ever put that smeared stuff on that forms that like little skin over the wart, it's basically salicylic acid. We can use it for muscle and joint pain. Plantar warts is the main thing I've seen it used for. And then zinc oxide, again, I've seen this used mainly for dermal ulcers. So then the next question is, Mr. McKeever, why did you give us this whole list? This just seems stupid. Yes, it does seem stupid. Do you need to know what everything is used for? Probably not. Do you need to know what dexamethasone is used for? Absolutely. There will be questions on your boards about dexamethasone. I can guarantee it. But what about the rest of them? Are they going to ask you what to use acetic acid for? Probably not. But what they might ask you is, what is the charge or the polarity of acetic acid? So you definitely need to, by the time you graduate, correlate those two columns. So knowing that calcium chloride is a negative. Now, the good news is if you look at this, most of the medications you're going to encounter that they're going to ask you questions on are negative in charge. And then I get the question, well, why is that important? Why do I need to know what the charge is? Well, remember I told you with iontophoresis, it's delivered via E-stim. What do we know about charges? Yeah, exactly, Josh. Know what pads are, right? So I've got my negative pad. Wait, I'm positive pad, right? I'm sorry. And here I got my negative pad, right? Or my negative terminal. What do we know about charges? What have you always heard with magnets and stuff like that? Yeah, right. Opposites, negative and positive, attract each other. If they're the same, they do what? They repel. Good, right? So if I have a, let's say we're talking about dexamethasone here, which is a negative charge. I'm going to put that, so here's my, I'm going to put that under that negative pole. Because what's going to happen is this pad is going to be charged with negative ions, and that's going to push that medication because it's going to repel it from that pad, and that's going to push it in the skin. The other thing I can do then, let's say I'm working on lateral epicondylitis. So that's out here in that lateral epicondyle of the humerus, right? The other thing I can do is then put the positive pad on the other side, and that can help pull that medication into the skin. So we're going to use that positive and negative kind of idea to deliver medications. A little bit higher than you need to know for physics. The main thing I want you to remember is that dexamethasone is used for inflammation, and it is negatively charged. There might be a question on that coming up. Dexamethasone is negatively charged. It's deal with inflammation. Hint, hint, Bob's your uncle. But for your boards, they may ask you a question where they'll say, you know, you're treating a dermal ulcer with zinc oxide. What pad on the iontophoresis machine would you want to put the zinc oxide? Well, zinc oxide is positive, so you're going to put it on the positive pad because you want it to repel that from that pad to be delivered into the wound itself. Does that make sense to everybody? At least the charges. Again, don't worry about everything. Okay, good. There we go. So we know that compositions of living things include the following 5 elements. Oxygen, right? Most living objects have oxygen or give off oxygen in the case of plants. Carbon, right? To be classified as organic in chemistry or biology, the object must be carbon chains, right? So that includes carbon and hydrogen. Hydrogen, nitrogen, and calcium. So when we have, and this is getting a little further than what Dr. Johnson got into it. When we have an atom, right? So we have an atom, and we have our nucleus, right? And then we have our electrons out here in our valences. In the nucleus, what's in there in the nucleus? What parts are in the nucleus? Well, yeah, protons, right? We got our protons. What charge are protons? Positive, good, right? So we've got our P positives and our N neutrons. The more molecules or the more parts of the molecules that we have in that center part of the nucleus, the denser the molecule. Does that make sense? So the more neutrons, protons stuff we have in there, the kind of the larger the molecule gets. That's why when you follow that periodic table up, right, as that nucleus gets bigger, the element gets larger. So we have that those protons there. We also have out here our little electrons, right? And the electrons are what's responsible for maintaining the negative balance. So we have the positives and the negatives. And if for an element to be completely neutral, you must have both positives and negatives equating with each other, right? So you must have enough electrons to match protons. There are these other particles called quarks, and that's getting into more theoretical physics. I'm not going to ask you to understand what a quark is, or really even, we'll talk briefly about photons when we talk about light, but this isn't a physics 200 or physics 300 class, so don't totally think that I'm going to make talking about quarks. So we're not going to be talking about string theory. I may mention it, but we're not going to study string theory and stuff like that. The main thing you need to know is neutron is a neutral particle. Proton is a positive particle, right? And electron is that negative. As long as there's enough electrons to match the protons, the atom itself remains a fairly neutral charge. The electrons you learned from Dr. Johnson yesterday, right, likes to have a specific number of electrons in their orbit, right? You remember talking briefly about that? Yes, it was yesterday, it was the other day. That in that inner orbit, the one that's closest to the nucleus, right? In what we call, so when we're looking at these and we're talking about these in physics, what we say is, this is orbit 1. This is orbit 2. Or the other term we use for that is valence. So those valence electrons. So in orbit 1, atoms like to have 2 electrons to be kind of stable element. In orbit 2, they like 8. In orbit 3, they like 18. Orbit 4, they like 32. Orbit 5, they like 32. Interestingly enough, in orbit 6, they go back down to 18. And in orbit 7, they go back down to 8. One thing I noticed there that always struck me when I was going through physics is electrons like to be in pairs, right? There's always an even number down here because electrons kind of like to travel in pairs. So if I have 2 electrons, that gives me a pair of electrons there. If I have 8 electrons, I have 4 pairs of electrons. What happens, let's say that we've got, let's add another proton here, and we'll add another electron out here in this outer valence. So that atom there, I'm not going to, we're going to stay, or I'm going to keep going. In that atom there, that is a stable atom, right? Because protons are equal to the electrons, right? I've got 3 protons, I got 3 electrons. But looking at that, remember, I said that second valence likes to have 8 electrons. So while this is stable, this element is going to try to seek out a partner to make that outer valence stable. It's going to go, I'm kind of happy, I'm neutral, but man, I could really live with a partner, and that would make me very happy. And so this atom itself is going to try to seek out something with 7 electrons in its outer valence, right? I'm going to talk about ionized in a second, Josh. This one's not quite ionized yet because it has equal parts, right? It has equal electrons and protons. But it just doesn't like the way it's sitting because it doesn't have a full valence in its outer shell. So it's just basically saying, I'm happy, but you know, I do a lot better when I'm married with something else. Now, if for whatever reason, this outer valence electron breaks off, and now we have more protons than electrons, what Josh brought up is, at that point, this becomes an ion. because now I have more protons than I have electrons. I have a positive charged atom. Or if vice versa, if for some reason I pick up an extra electron or an extra 7 electrons, that becomes an ion again, it just becomes a negatively charged ion. And so that goes into a little bit more theory than we're talking about. But looking at this kind of looks at what happens the bigger we get in an element, right? So the element itself is, the size is determined by the size of that nucleus and then also the shells that it has around it. As nuclear charge increases, the electrons are added to the outer orbits and their inner orbits kind of shrink in. So this is interesting because what this helps prove is even at the atomic level, we can actually see an effect of gravity. Because if I've got an atom here with a nucleus being this green thing, and I start adding outer valence electrons, those inner valence electrons get closer to the nucleus. And they become more attracted to that nucleus, so their valence gets smaller. And that's to allow for more of the other valence to get on so they don't lose charge and pop off. So an ion is a charged atom, right? Where if we either lose an electron or gain an electron, it either becomes positive or negative. So if an ion loses an electron or has a deficiency of electrons, it's a positive charge. If an ion gains an electron or has more electrons than protons, it's a negative charge. And then we have isotopes. Isotopes are interesting because isotopes are atoms of the same element with different numbers of neutrons. They typically have identical behavior. So if I have something like hydrogen, we go back here to hydrogen real quick in the chart, right? Hydrogen just has 1 electron and 1 proton. It's a kind of very small atom. But if it gains a neutron, because it doesn't have one naturally, it then becomes an isotope of hydrogen. So neutrons are kind of this, I mean, it used to be foreign type particle, but we now understand a lot more about neutrons. And actually, to the point that we're now actually looking at developing things like neutron bombs, which to me always terrifies me. It seems like every time we find something in science, we try to find a way to weaponize it. But the more neutrons that atom gets, the greater their mass number, the total number of protons and neutrons in the nucleus get, right? So an iron isotope with 26 protons and 30 neutrons would be a 56 mass, or what we would call iron 56. So that leads us to compounds. So when 2 atoms of different elements bond to one another, they make a compound. Compound is different than an element. If I just have O2, that's still an element because everything is oxygen. If instead I have CO2, so this is an element because it's just 1 atom, just multiple of them. This is a compound because now I've got multiple atoms coming together to form together. Typically, compounds can only be separated into its separate parts, constituent parts by chemical means, right? If you take salt, you can't take out a knife and cut the salt particle and break apart the chlorine and the sodium. There has to be a chemical reaction or something to either suck the chlorine off the sodium or suck the sodium off the chlorine in order to get an element like that. And it's really funny when you think of salt, because again, it's kind of, these are thoughts that go through my head when I think about this. Sodium chloride, right? NaCl is salt, your typical table salt. Either of these elements alone are extremely dangerous to our body, right? If we have sodium separate and it mixes with water, you have boom happening. You have an explosion happening. Typically a very, very violent, flamey type explosion. Chlorine is in bleach, right? Chlorine is also, again, I'm a huge World War II and World War I buff. What did we use chlorine for in World War I? Does anyone know? Mustard gas, yeah. right? One of the deadliest forms of warfare we've ever done. Does anyone know why it was called mustard gas? I'm sure Josh probably does. Yeah, it was yellow. Exactly. And so chlorine itself, if chlorine gets in your lungs, it literally burns your lungs. Have any of you ever cleaned like your bathroom and you accidentally, like you put bleach in the toilet to bleach the toilet? Yeah, thanks, Jeremy. You put bleach in your toilet to bleach your toilet and then maybe accidentally mix it with some cleaners and all of a sudden your nose is burning. Anyone ever encounter that? Yeah, right. What that is that's mustard gas. That's how you know it's clean. Yeah, when my nose is burning, it's clean. I don't know about that, but yeah, right. So chlorine gas is actually very deadly to humans. There have been multiple cases of people that are, housekeeping staff and stuff like that, that have literally passed out from chlorine gas when they're cleaning restrooms or something like that. So it can be really dangerous. There's a great story if you for any of you that might be, I'm going to talk about that in a second, Alec, why is chlorine in a pool? If any of you are ever interested in kind of looking at the horrors of chlorine gas, there is a story about a battle in World War I at the Auschwitz forest in Poland. I believe it's on the border of Poland and Russia, if I remember correctly. I don't know if any of you ever heard that battle, but it's an interesting battle. The technical name of the battle is the Battle of the Dead Men, because there's a bunch of troops, Russian troops and Polish troops that were holding the fortress, and Germany came in and basically turned on giant fans and blew all kinds of chlorine gas into the fortress. And the chlorine gas literally attacked the people that were in the fortress, and their eyes were literally melting. They're coughing up blood. And so they actually charged out of the fortress in one last gasp attempt, and the Germans actually retreated because they thought they were zombies coming after them. Because the people were literally coughing up bits of lung, they had blood flowing out of most of their orifices. It was kind of a scary time. Thanks, Germany, exactly like Josh said. But then chlorine in a pool, Alex says, well, what about chlorine in a pool, right? Well, chlorine in a pool technically, right, is a compound. We have it in a compound. A lot of times it's mixed with, I'm trying to think, it's calcium chloride, I think, that goes in the pools. But why do we use chlorine in a pool? Well, we know that if chlorine would kill our lungs, it also kills any bacteria or virus or fungus or something like that, right? That's why we put chlorine in a pool. That's why if you own a pool and you shock the pool, you're not supposed to get in the pool right after you shock it and give it a high level of chlorine, because again, it can burn your lungs. But at there are levels, right? That's why you're supposed to check your pool levels, right? And there are levels at which chlorine is safe. It is a little bit harmful when it gets on our skin but that's why we check those chlorine levels, Alec, because we want to make sure that those chlorine levels aren't harmful. That's why they have those test kits. And they'll tell you, is the pool safe, or do you need to add more chlorine, or do you need to add more base in order to bring that chlorine level down? And again, it could do some good things for your skin too. If you've got like acne, the chlorine, obviously acne also has a little bit to deal with bacteria on our skin. So it can actually clear up a little bit of acne as well, but it can dry out your skin really bad, right? It's why it's a good idea after you get out of the pool to shower off, just so that your skin literally doesn't dry and crack. But yeah, definitely it can be harmful when we get it on our skin, but that's why we have those chlorine levels that are set to be safe for humans, right? Now there are alternatives to chlorine in pools, right? There's all kinds of, I was at a pool in, I think, San Diego, that was a brine pool. Yeah, saltwater pool, exactly. And there's all kinds of alternatives to that. So, but chlorine by far is the easiest way to kill Pseudomonas aeruginosa, which is the main kind of bacteria that gets in pools. That's the hot tub disease pool. So compounds are when atoms join together, right? If a substance just is mixed together without chemically bonding, it's called a mixture. For example, air, right? You're breathing air right now in and out, right? But all that air that you're breathing in isn't just oxygen. There's some carbon dioxide in that air. There's a lot of nitrogen. I think 70 or 75% of what we breathe in is nitrogen, because the molecules are larger. There's probably a little bit of argon. There may be some helium. There may be some carbon monoxide. There are all kinds of things in the air that we breathe, right? That is a mixture. Those molecules aren't bonding together. They're constantly bouncing off each other. If you take water and you put salt in it and you stir it up, right? That salt doesn't bond with that water, but it dissolves in the water and becomes a mixture. If you let that salt water sit for a long period of time, eventually that salt's going to kind of illuminate down at the bottom of the cup. So again, two molecules that are bonded together, right, are a molecule. Then when we combine different stuff together, we get compounds. And then we kind of get out there. I always thought that oxygen or water, when you see it, it kind of looks like Mickey Mouse, doesn't it? Just that smiley face to him. That's literally what that water looks like at the atomic level. Looks like a little bit Mickey Mouse type. H2O, some high quality H2O. So when we get a chemical reaction is where an atom's rearranged to form different molecules. Where you pull molecules apart, it's going to require a little bit of energy. But in something like photosynthesis, where the plants bring in that carbon dioxide, right? So plants breathe in carbon dioxide where we breathe in oxygen. We breathe in oxygen, give off carbon dioxide. Plants breathe in carbon dioxide and give off oxygen. That means we have a symbiotic relationship with plants. Does anyone know where most of our oxygen is made in the world? For the whole world. It's got to be a large area. Yeah, the Amazon. Exactly, Josh. Good guess. Was that a guess or did you know that? Did you hear something? Jeff Bezos. Okay. Yeah, the Amazon provides us with most of the oxygen we actually get in the world because it is such a large swath of plants, right? And unfortunately, we're kind of destroying that swath of plants, right? So there's a chance that we could harm ourselves in the future, right? There's all kinds of wonderful science fiction movies about that. But plants themselves they breathe in that carbon dioxide. During photosynthesis, by using the sunlight's energy, they split the carbon and that gets absorbed into the plant itself and helps the plant grow. And the oxygen, and they give off the oxygen as a byproduct. And then that oxygen we breathe in. And then eventually we probably pick up that plant, if it's lettuce, grab the plant out of the ground and then we eat it and then we consume the carbon that's in the plant as well. So plants really do provide us with a symbiotic relationship. Even if we don't eat the plant, if we eat cows because we want to have a hamburger, that cow probably ate that plant, which consumed that carbon, which then came to us in the form of proteins. So plants are kind of important, I'm just saying. When we combine atoms, it releases energy, right? Oxygen's atoms combine with iron to form rust. And if you're ever able to watch a slow motion capture of something rusting, you can also see that it's a chemical reaction because it gives off a little bit of heat, right? And it's a really minute amount, but you can actually catch it on a thermal camera if it's capturing it really slowly. Interestingly enough, even in our body, when we bring in oxygen, oxygen is our #1 free radical in our body. It oxidizes a lot of our tissue, which is a good thing for providing energy, but can also damage us if we have too much. And some of you have probably heard where we take antioxidants. Has anyone ever heard that before? Certain vitamins are antioxidants, right? And what they're really designed to do is keep our oxygen levels in our body at an acceptable level. The funny thing is if you already have a deficit of oxygen, maybe you have COPD or something like that, taking an antioxidant is probably not a good idea because you're already low on oxygen, just saying. So matter versus antimatter. Again, we're 1,000-foot level. You're not going to get into the weeds with this. Matter is composed of atoms with positive nuclei and negative electrons. We know that antimatter exists, and antimatter is just the opposite. In an antimatter, the negative nucleus combines with positive electrons, or what's called positrons. Both matter and antimatter cannot exist in our environment, especially at the exact space and time. And this is the theory about what creates black holes. A lot of our theory on black holes, and again, it's theory because we obviously haven't visited one yet, except for Matthew McConaughey. He's been through a black hole before, right? We're pretty confident that when matter and antimatter collide, it creates black holes. You would think that, Alex. So Alex says a positive electron is positive, so it wouldn't be a proton. Yet what we do is we actually change it. We say that if the electron is positive, we call it a positron. And then if the proton is negative, we call it an antiproton. That would be just, it would be way too easy if we just called them the same thing. Science has got to make it hard for us. I'm just saying. And again, this is really kind of higher level physics, and the book talks about it, so I just briefly talk about it as a requirement. You're not going to have to define the difference between a proton and an antiproton. They're just opposite charges. This stuff can be scary, though. I mean, there's a lot of theories that show that if antimatter and matter come into contact with each other, it could theoretically end all life on Earth. So, yeah, I don't know that we want to do that. I kind of like living. I don't know about you guys. And then we also have this stuff called dark matter and dark energy. Right? Dark matter is unseen, unidentified matter from different elements that comprise about 23% of matter in the universe. We haven't sampled dark matter yet because we haven't gotten the ability to travel that far. Most of the dark matter that we know exists in the universe is multiple light years away. One of the side effects of dark matter is this thing called dark energy. Dark energy is anti-gravity energy. So if gravity attracts, that means anti-gravity is going to repel and push things away. And finding the nature of dark matter and the nature of the energy of empty space are high priorities in the quest, right? What we know in 2050 probably will dwarf what we've ever known now, hopefully. And we'll know more about this stuff because it could be the key to us actually doing space travel. Because right now, let's say that we wanted to take a trip to Mars. What's going to be the major problem taking a trip to Mars? It's not going to be the energy to get there. Yeah, it's going to be the time, right? I want to say it's 40 years or something like that to get to Mars if we take it the way we are right now. I could be wrong. Maybe it's less than that. Maybe it's 20. It might be 20 some years. But figure that if I decided that I want to get on a flight to Mars, by the time I get there, I'm going to be too old and feeble to help out. Right? So that means if we're going to send something to Mars, like if for whatever reason, good old Bezos develops a rocket ship to send to Mars, he's technically going to have to send pretty young people. Right? He's going to have to essentially send kids in order to travel. Is that the one that he's developed the space? He's got the theory of developing the space elevator for? I've read about that. Yeah, it's still a little bit of a pipe dream for him. Let's start putting more stations in space before we get there. I think the more logical conclusion would be developing something like that on the moon than it would be in space. But yeah, so Elon's making a space hotel. Here's my question for that, and this is just a personal opinion. This does not represent the views of Pima or anything like that. How about before we develop a space hotel, we feed all the people that are hungry in the world? I'm just saying. I mean, don't you think that's a little bit better of a goal? Or maybe we solve climate change. Just saying. Because let's face it, Alec, by the time a space hotel is built, are we going to be able to afford to go there? Yeah, right? No, we're not going to be able to go there. The only people that are going to go there are people that are stupid rich. And maybe you're stupid rich. Maybe I'm just making a base. Yeah, that's going to be, Josh is right. Josh says military base on the moon to establish dominance. I'd be willing to bet that's the next thing we see. Because the first, figure it out, is the first, not planet, the first country to establish a military base on the moon can basically carve out a swath of land, right? It's, for those of you that have ever studied stuff like this, it's basically the Antarctic race all over again. Because that's what we did in Antarctica too, is we put bases on Antarctica so that other countries couldn't take over Antarctica. Yep, exactly. Right. There's all kinds of theories on that, but Josh is right. Eventually, the military base on the moon will probably be the next thing. right? Space Force will go there. Don't even get me started on that. Why did we just not use the Air Force? So some properties of solids. We're going to talk about solids, liquids, and gases. We're probably not going to get through all of this. So let's finish the solids and then probably call it for the day. So if something is solid, they're typically arranged in a regular array called a crystal. Right? Solids that do not have atoms arranged in a regular array are called amorphous solids. So they're more fluid solids. The interesting thing about solids is solids have density. Whoever gets there first owns it. You're right, Mark. Yep, that's literally the way it works. Right? You and I could get up there and claim the whole moon, technically. And just remember, on the dark side of the moon is where Pink Floyd lives. Anyway, so our solids have denseness, right? It's the ability to consume volume. Right? Density is the mass by the volume. The opposite of density is porosity, which means having holes in it, right? Some structures have more space between particles and others have less, right? Fats in our bodies are solid at room temperature, right? And then if we turn them into liquids, if we heat them up, right? Or fats that are solid at room temperature are denser than fats at liquid at room temperature, right? But also, if we heat up those fats, even if we take a chunk of our own adipose and heat it up, it will turn to liquid. But we use a lot of fats in our cooking, don't we? Because olive oil is technically a fat, but it's a liquid. But butter is also a fat, and butter is a solid. Well, that's just turns upon the density of the actual material. Iron, or as I'm trying to say it as a way people say, iron is a lot more dense than wood, right? If we build a house out of iron, it's going to stand this test of time versus the house that's made of wood. When you look at all the structures of the ancient world, right? So you look at stuff like the pyramids at Giza. The big one I'm reading about right now is Göbekli Tepe in Turkey. The Acropolis. All of those structures, they're not made of wood, are they? They're made of pretty dense, usually sandstone or something to that effect. And they've stood the test of time. Right? Think about that for a second. Think how long ago the pyramids at Giza were built. And we still can see them today. What about the house you live in today? Like, so the house that you live in, Mark, in 300 years, is that house going to be there?
No.
Yeah, probably not, right? It's probably not going to be there. So my headset turned off. I apologize. Right in the middle of you talking, that's great. So yeah, so the denser structures tend to stand the test of time. Again, the one I'm reading about right now, Göbekli Tepe in Turkey, is actually changing our whole concept of what we think of the ancient world, because Göbekli Tepe was built as a city during a time period where we thought people were just hunter-gatherers. Actually pretty interesting. In the human body, density can change because we're cellular dynamic beings, right? Bone can become more and less dense. As we get older, our bones become less dense. They become more porous. That is where osteoporosis comes from. And so need is the primary stimulus for increasing density, right? We teach our tissue to change by doing what we do. So how do we make our tissue more dense? We move. In the human body, movement is key to maintaining density of the bones. Also taking in proper nutrients, right? So just looking at this here, right? This first picture shows you, here's what a normal bone looks like. This is what a bone looks like with osteoporosis. And actually, this is actually an X-ray I have from one of my patients from a long time ago. It's not the one from my patients in the lecture. This is actually, I stole from a book. But look at all those holes in that spine. What do you think that predisposes this person to? With all those holes in those vertebral bodies? Fractures, yeah, right? This is a patient, I'm not joking, I know Dr. Johnson talked about this, but this patient over here is that patient that, yeah, literally blown away, right? The patient that sits down in their chair and they break their back. And they're like, all I did was sit down. Well, because the bone is so porous, it doesn't take much to fracture it. Yes, Mark.
When it gets to that point, is there any type of building it back up or any exercise that would actually begin to help that? Henry?
At that point, the best we can do is slow the process down.
Right.
Right. And we can give, there are certain medicines now that we have that, like Boniva is one of the big ones. There's certain medicines that help speed along calcium reabsorption. So it's not going to ever cure the osteoporosis, but it might make the bone less likely to fracture.
Right.
So yeah, once we're at that point, we're pretty much a done deal. And Ariana asked about microfractures, right? So microfractures where do microfractures typically occur? Do they occur in the outer parts of bones or the inner parts of bones?
Outer.
Yeah, the outer parts, right? Exactly. In that kind of periosteum region. And a lot of times what that has to do with, Ariana, I mean, there are a couple of reasons you can get microfractures. I mean, you could be doing something stupid, like, I don't know, doing plyometrics when you're not quite ready for plyometrics or something to that effect. But a lot of times that's just kind of that outer part of the bone not having enough calcium absorbed yet. And unfortunately, microfractures typically occur in women. We're going to find out that for whatever reason, bones don't like women very much because of the hormones in your body. And that causes your bones to be more predisposed to stuff like fractures because of osteoporosis. Estrogen is kind of a nasty chemical. It's really useful for you guys, for us to continue as a species, but it does some kind of nasty things to your body. And I sometimes go, wow, that's not fair to women. So there are all kinds of bonds that are out there. There's ionic, covalent, metallic, van der Waals bonds. I'm not going to make you memorize what each of these bonds mean. Okay. So don't totally freak out. We're not going to go into, even if we go to van der Waals bonds, you're going to be like, what are you talking about, Mr. McKeever? You talked briefly about ionic and covalent bonds with Dr. Johnson. Metallic bonds, you should be able to figure out metals form metallic bonds, right? And if you get a lot of metal bonds together, they form metallica. Just kidding. Those are typical bonds that they form. Let's actually stop here. It's 51 after, so I don't want to take up too much time. We'll pick this up next class, which would be Monday. Let me get out of my lecture here because you guys want to get some lunch, and I don't want Mark getting mad at me. I can see he's already getting hungry. All right, so I'm going to stop recording. That is it for the day, guys.